So this one, page 65, is talking about an actual hypothesis test related to the t-distribution, right? So the breakdown that we're looking at here involves assumptions. You always have assumptions, and the assumptions are generally keys for us to get a sense of what type of hypothesis test we should be working with. And in most cases, we'll see simple random samples. So it's kind of like, well, if that's an assumption for all of them, we can sort of disregard that one because it's not going to help us narrow things down. All right. Sigma is unknown, so we use S instead. And it's approximately a normal distribution, or the n value is greater than 30. All right. Either way, because once you hit the benchmark of 30, you can go with a z distribution or a t distribution. They're both going to accomplish the same thing. So what I have encouraged people to do is just kind of, for when you're testing a claim about a mean, don't even bother with a z distribution because a t distribution is going to cover all the bases anyway. All right. The null and alternative hypotheses are going to take on the same role as they did in the previous hypothesis test. So that should be pretty okay. It's all going to be dependent on the structure of the problem. So you'll be able to pull that from the information in the word problem. The alpha value is either going to be given to you or you're going to select a 0.05. Then since we're looking for the p-value, and this calculator is going to give you the p-value, so that's good news. If the p-value is less than whatever the alpha value is, you reject the null hypothesis. All right, so it's very procedural, and that's what I was saying before with the whole, t-test, z-test, like the origin stories being rooted in calculus. Because calculus isn't a prerequisite for this material, there's a lot of things that we have to take on faith that it's all correct. But then on top of that, we sort of have to look at it like, well, if we're not on the hook for the underlying theory, then all we can do is just follow the steps, right? So it's unfortunate for a lot of folks, especially the ones who prefer to understand a concept, the underlying concept rather than, just regurgitate facts. This is more at this point, regurgitation of facts. And I would even say that until I started first teaching this course, then got into some, independent studies on my own of some higher level calculus, I really didn't understand the underlying theories behind a lot of these steps, right? So it's a journey for a lot of folks out there. It's not a necessary journey, but the problem is, if you don't at least try to understand some of the theory, then it's honestly, it's like handing a toddler a butcher knife and hoping for the best. It's really just like that, because when people publish results of studies with like world-changing consequences and it's wrong, it's disastrous, right? So policy change based off of this kind of stuff. And I know a lot of instances. I've seen them on the news. I've even heard it from colleagues where information, if you make it sound intelligent enough, then it gets accepted as fact without any like investigation whatsoever. Well, that sounded smart, so it must be true. That's what happens when you get into statistical analysis, right? So the complete graphic calculator approach, you can see it. It's the Desmos Test Calculator. So let's get into an example. The time it takes for students who drive to school. And by the way, I made this problem up myself, so that's why it seems very particular to a high school. And it's also kind of sophomoric. The time it takes for students who drive to school on a daily basis to exit the school from their 8th period class. The end of the day was 8th period at that time. Start their car and exit school grounds approximates a normal distribution. On February 3rd, 2003, a teacher who had nothing better to do timed a sample of 45 student drivers and determined the mean to be 5.7 minutes with a standard deviation of 2.1 minutes. Right. So what that's giving us, and I'm just going to jot this off on the side here, that's giving us sample data, right? And specifically, it's sample statistics. It actually isn't raw data. It's data in the sense that it's a set of numbers, but they're actually statistics, right? Summary statistics, right? So we're looking at an X bar, the mean for these 45 individuals is going to be the 5.7 and a standard deviation of 2.1, right? Referring to the sample of 45 student drivers. All right, so we have N is equal to 45, X bar, sample mean is 5.7, and S is 2.1. The only thing you got to be cautious about when it comes to something like this is the units. You know, I'm not too big on messing around with that sort of thing, especially when it comes to like obscure units. You know, like if you start getting into, oh, I forget, it was a problem I was doing in another class. It had to do with, oh, I think it was cholesterol. It was like milligrams per deciliter. You know, it was like, you know, I'm not going to mess around with units like that, you know, like conversions or anything along those lines. But hours, minutes, seconds, that's fair game. So you just got to be careful because sometimes the question might say the mean is 5.1 or 5.7 minutes with a standard deviation of 45 seconds. So you'd have to convert that to minutes and say 0.75 minutes. You know, just something very slim. Use a 0.01 significance level. All right, so 0.01 significance level. So that's the alpha value. So you could just tuck that into the box. Now, when it comes to doing this on a test, I'm gonna still kind of adhere to this structure. It's just gonna look a little different because getting a flow chart like this on Blackboard is like a nightmare. So the way I'll end up doing it is a kind of fill in the blank sort of question. You know, so fill in the blank with your null hypothesis, fill in the blank with your alternative hypothesis, fill in the blank with your alpha value, you know, and that sort of thing, right? So just so you have a little bit of context. All right. Test the claim that the mean time it takes for students in general to go through the above routine is actually greater than 5 minutes. All right. So looking at our possible null and alternative hypotheses right up here in step 1, greater than, a greater than symbol corresponds with an alternative hypothesis. That's not a greater than symbol. A greater than symbol corresponds with an alternative hypothesis. All right. So when they say test the claim that the mean time for students in general, the in general part is implying a population. Right. Because we're not talking about just these 45 students. We're talking about all students, which is referencing a population. So they're saying test the claim that the mean for a population of students is going to be greater than 5 minutes. All right. The greater than symbol corresponds with the alternative hypothesis. Mu is the symbol that we use for a population mean. We're trying to say in this case that mu is greater than 5 is the alternative hypothesis. All right. Now it's kind of weird to write an alternative before a null. Or at least it feels weird, but it's actually pretty ordinary, all right? Because the null hypothesis is what you would consider to be the status quo or the standard value, the assumed value, the ordinary value, what has always been the case, you know, and this is what we're trying to say is now the case. You know, in the past, you know, we would think that, you know, students, you know, like in the old TV shows and movies, the 80s ones, where the bell rings and at the end of the school day and there's like an army of students coming running out of the front doors of the building, and they're scattering and they're at a full sprint. That's kind of what you visualize. So it's like there's no way it takes more than 5 minutes for students to get out of school. you know, but maybe these days they're hanging around a little longer for whatever reason. You know, maybe it's sports, maybe it's just because they want to. You know, there are all sorts of different possibilities. Maybe they just have a crappy parking spot and it just takes them a long time to get there. A lot of different possibilities. And the only difference between the null and alternative hypothesis is the sign. All right. So if you look carefully here, we have a mu and we have a 5, but we have a greater than symbol. The mu and the 5 are going to carry over. The only difference is that we're going to have an equal sign here. All right. So something to be mindful of, the null and the alternative are not opposites of one another. They're just alternatives to one another. All right. So you can think of plenty of instances in which you're looking at two options that are not necessarily opposites of one another. You know, you could look at it like, all right, I'm pulling out of my driveway in the morning and I'm going to make a left. All right. That's an assumption. And then somebody would say, okay, well, what's the alternative to that? And somebody else might say, well, clearly right. You know, like if you're not going left, you're going right. No, I could be going forwards. I could realize I forgot something back at the house. I could go backwards. You know, there's a lot of, I was going to say a lot of different possibilities. I mean, a lot of possibilities limited to what's available in terms of choices when you're driving a car. All right. But just because you're not going left doesn't automatically mean that you're going right. All right. So just because you have an alternative hypothesis that's greater than doesn't mean that the null is going to be the opposite of that and it's going to be less than or equal. What we're looking at for a null is some assumed value that we're going to default to if the alternative is not true. Right? It's kind of like our reset. If you're flipping a coin, for example, the assumed value is a probability of 0.5 for heads. Right? So if I say, no, this is a trick coin, the probability of heads is way more than 0.5. It's like 0.8. Then just because I didn't prove that it's 0.8 doesn't mean it's now somehow way less than 0.5. It doesn't mean that it's like 0.1 or 0.2. I would just say, okay, well, if it's not unfair, it's probably fair. Fair would be 0.5. I just kind of snap right back to the default. Right? It's like a reset. Right? But that alternative hypothesis tells us the type of tail that we have on the test. Right? Because the arrow here is pointing to the right, it's a right tail test. All right. And so hopefully you're noticing some familiarity based off of the fact that, you know, in the previous hypothesis test, it's the same idea, except now we're working with mu's versus p. You know, instead of having a population proportion p, we now have a population mean of mu. Right? But that's so far, it's been the only real significant difference. Right? We have a 0.01, so I can start getting into my Desmos calculator. I could slide that over to 0.01. The sample size, an n value of 45. My slider doesn't go large enough. So what I can do there is I just tap on the 30 and make it go to 45. That's not a problem. All right, degrees of freedom are automatically computed for you. We need critical values. That comes from the idea of what kind of test it is. Is it right-tailed or left-tailed? Right. So the critical values they make up part of the graph. Right. So we're looking at a bell-shaped distribution. Now, since the n value is greater than 30, we can assume it's going to have a generally normal shape. Now it's a right tail, which means that all of the alpha, all of the area associated with the alpha value is going to be in the right tail. So what we need is a critical value associated with that location. Now I have the Test Calculator set up to give you those numbers, right? So we just have to write it down and conceptualize it. So if you hit the drop down for critical values, you see an option for a left tail, right tail, and two tail. So ignore the left tailed and the two tailed and focus only on the right tail, right? If you typed in or scrolled to these values correctly, the alpha and the n value, then whatever number you get here, regardless of the notation, it just looks kind of funky, that's going to be the correct value. So in this case, 2.414. That's the cutoff for the rejection region. All right. So that shaded region here, that's the rejection region. All right. And what do I mean by rejection region? It's the location where if the test statistic falls in that region, that means you reject the null hypothesis. All right. We're not there yet, but that's something to be mindful. All right. So when you're done with that, I recommend that you close that folder so that it doesn't get overwhelming. So then we get into the critical region graphs. Again, broken up into left-tailed, right-tailed, and two-tailed. This is a right-tailed situation, so I'll turn on the right-tail graph. All right, and you see it shades off into the right tail over here. All right, you see it's a little teensy tiny little bit of shading, way less than what I shaded, but you know, it doesn't have to be perfect. So once you've accounted for that, and all that's going to do is just make your diagram look more appropriate, close that folder. Then we get on to statistics. So there is no function or no notation in Desmos for x with a bar, x bar. So I just made a subscript of bar. So that's the x bar that you see here. All right. So that number is a 5.7. So if you can scroll to the 5.7, by all means, otherwise just type it in. The standard deviation is 2.1. So obviously these are rounded values. There's no numbers in real life ever work out this cleanly. Yeah, I'm having a hard time getting it to land on a 2.1, so I'm just going to type it in. So I have my sample mean, my sample standard deviation typed in correctly. Now I don't want to accidentally screw anything up. So once I have those in correctly, close the folder. Now parameters, there's only one parameter, right? The assumed value of mu, right? The assumed value of mu is whatever you put into the null hypothesis, right? So this number here is the assumed mu, which we call mu sub 0. That's the assumed. All right, you have to have some sort of assumed value in order for a hypothesis test to work. So I'm going to slide my slider to that number and then close the folder. All right. Now the test statistic. So test statistic's weird in the sense that the notation that I'm going to use on paper is slightly different than what I'm going to use on Desmos. Every hypothesis test is going to have its own test statistic. This test statistic is in the form of t is equal to x bar minus mu sub 0 over s over the square root of n, which is a crazy looking formula. However, best I could, I got that into Desmos. Again, the x bar thing being an issue. So the test statistic will be computed for you as long as you put these numbers in correctly under statistics and parameters, right? So this number, this t, is your test statistic of 2.236. What we do, assuming that 0 is the middle of our normal distribution, well, in this case, approximately normal, what we're doing is we're looking to see if that number is going to fall in the shaded area or not. All right, we look at this as a glorified number line. So if you were to go out in this direction here, or quality arrow, you'd get to negative infinity. If you were to go out in this direction here, you'd get to positive infinity. All right, so 0's in the middle. It's just like a number line. You would be thinking, okay, well, where does that 2.236 fall? I have no idea. I just know that it doesn't fall in the shaded area, because you'd have to be 2.414 or greater in order to fall in the shaded area. So it's going to fall just shy of that. So what I do on my graph is just label it TS for test statistic. All right. And so based off of the placement of that number, we get an idea that this is not going to fall in the rejection region. And again, that rejection region is associated with the null hypothesis. So if it doesn't fall in that rejection region, then we would say do not reject the null hypothesis. All right, so that means keep the null hypothesis, get rid of the alternative hypothesis, because it's one or the other. All right, they're not opposites of each other, but it is a case of one versus the other. If you're not selecting one, you are selecting the other. All right, and then the only other thing that comes from this is the p-value. And again, it's based on whether it's a left-tailed, right-tailed, or two-tailed. The left-tailed, you can see a probability value is included there where it says t-dist. All right, 0.98, blah, blah, blah. Well, we're not doing a left-tailed, so ignore that. Right-tailed, we have a p-value, a probability value of 0.0152. All right. Generally, it's the p-value that's the driving force behind whether or not you're concluding in favor of the null or alternative hypothesis. If the p-value is less than the alpha value, you reject the null hypothesis. That's the statement right up here in step 3. If the p-value is less than the alpha value, you reject the null hypothesis. All right, so I'm looking at this number and comparing it to this number. And I would be asking myself, is that p-value less than 0.01? It is not. So we do not reject the null hypothesis. All right, so whether you get it from the graph or the p-value, it's kind of a double dip, but you still get the appropriate conclusion, but then we have to write it in words. All right, so the general structure is there is insufficient evidence to reject the claim that you state the null hypothesis in words, whatever the null is. In this case, mu equals 5. You'd have to write that in words in the context of the question that you're being asked at the whatever significance level. So in this case, the significance level is 0.01. So you can just kind of pop that in there. And then the second sentence addresses either the alternative hypothesis or the question that's being asked. Most of the time, the alternative hypothesis is the question that's being asked. So it gets covered, but sometimes you have to kind of take liberties with the conclusion format. All right. So what we're saying here is if we're talking about rejecting the null hypothesis, well, we're keeping the null. So there is insufficient evidence to reject the claim that the population mean you can paraphrase. What are we talking about? Leaving school, right? So reject the claim. There's insufficient evidence to reject the claim that the population mean time to leave school, population mean is the mu, is means equals 5 minutes at the 0.01 significance level. The question that was being asked, it says, test the claim that the mean time for students in general to go through the above routine is actually greater than 5 minutes. So there, we paraphrase that. Therefore, the claim that the mean time, because we now know what the mean time is in reference to, it's leaving school, is greater than 5 minutes. Well, this is the alternative hypothesis. I got a big old X right here next to the alternative hypothesis. So that's a pretty clear way of saying that that statement is false, right? And again, the calculator test is a t-test. But that is an appropriately framed hypothesis test. You know, it's a little dense. There's a lot going on there, but the more you do it, the easier it gets. It's just weird. And like I was saying before, it's uncomfortable. It's the kind of concept where you look at it and you say, well, I don't feel like I really did anything. Well, you're not supposed to have felt like you did anything. You're supposed to feel like you're drawing conclusions based off computations that were made for you.